Okay, so for the rest of today's lecture, we're just going to solve a couple more problems, give some examples of using energy conservation. We're just going to, since last chapter was work energy theorem, this chapter is energy conservation, we're now going to solve them all with the energy conservation equation. So the turkey here is in my way a little bit. Oh, here we can move him around. Oh, wait, he's not, how come he moves for me, but he doesn't move for you? Well, that's weird. All right. Anyway, so turkey. Okay, so the one other thing I should mention before moving on, well, not before moving on, something that we haven't done yet is we talked about the potential energy. Potential energy can be defined for any conservative force. We've got the potential energy due to gravity, which is mgh. Really important to understand that that's h. Whoops, I don't know why that moved. Potential energy due to gravity is mgh. H is defined as how far up we have moved from where we define the potential energy equals 0. So you just got to define your potential energy equal to 0 somewhere in your problem, and then we can define H as how far we've gone up from there. That's potential energy due to gravity. Potential energy due to springs. Potential energy due to springs, remember that the work done by a spring when you pull it out is minus 1/2 kx squared, so that means the potential energy stored must be plus 1/2 kx squared. So notice that the potential energy stored is plus 1/2 kx squared. And actually, regardless of which direction the spring moves in, whether we pull it out or push it in, we're going to store 1/2 kx squared of energy, right? So whether we squish a spring, you can't see it on, well, you can see my hands. If you squish a spring, boom, it's going to push outwards. You stored 1/2 kx squared. If you stretch a spring, it's going to pull back. It's got stored energy 1/2 kx squared. So potential energy due to springs 1/2 kx squared. So our total potential energy, if we've got springs and gravity, certainly is going to be mgh plus 1/2 kx squared. But if you've got no springs, then the potential energy due to spring is 0. If you've got no gravity, potential energy due to gravity is 0. I neglected to say where x, well, so let me write this down. H is measured up from defined 0, where you define the 0. In this, and for this potentially due to springs, where's x measured from? You know where x is measured from. Where's it measured from? Tell me, I can't hear you. What? I can't hear you. Okay, you're right. X is measured from the equilibrium position. Not equilibrium, yes, sorry, is measured from the equilibrium position. X is measured from equilibrium. The equilibrium position of the spring. So we will have to define, in this case, the potential energy to be 0 when the spring is in its equilibrium position, where it's in its position where it doesn't want to move. Okay, so let's go ahead and do a problem with springs and gravity, or at least with springs. Actually, let's do the problem. Let's see if we can get, now we can get rid of the turkey. Let's do the problem that we were doing in class the other day. Let's do the spring-loaded gun or the spring-loaded platform or spring-loaded anything that can shoot a projectile. So let's say that we've got a spring-loaded platform and we can put a projectile on it that will shoot upwards. And let's go ahead and say that it's in its equilibrium position. Let's put a mass m on a spring, on a platform on a spring k. And the equilibrium position is wherever it is in this picture here. And we want to shoot this object, so we're going to compress the spring, right? So think spring-loaded gun, a Nerf dart gun. We're going to compress it so that we can compress it some distance delta x from equilibrium, and so that when we let go, the object is going to be shot upwards. We let go, and then the object comes off the platform and goes up to some maximum height, which we'll call h above the equilibrium position of the platform. Oops, I meant to put that platform at the equilibrium position. Okay, so hopefully you understand the situation. We've got a spring-loaded platform. We put an object on it, push it down, let it go so it can shoot upwards. And the question is how high from the equilibrium position does the object go? Okay, so here's my problem. I wrote it out. It gave it some numbers. If the mass is 20 grams or 0.02 kilograms, the spring constant is 17. That's a 17 newtons per meter, and we compress the spring 1 centimeter. I guess I'm not compressing it very far. And let go from rest. How high does the object fly if once it flies off the platform? That's the problem we're going to solve. Okay, so I just turned the object into Jack, or it's a square Jack. Jack the jackalope. Okay, so anyway, so in order to do this problem, we're going to do an energy conservation problem. And energy conservation, right, says that if there are no non-conservative forces, then the total mechanical energy is conserved. Remember, that's what energy conservation says. If there are no non-conservative forces, the mechanical energy is conserved. And in this case, we are going to ignore friction unless you're otherwise told. You're going to ignore air resistance, so mechanical energy is conserved. PE initial plus KE initial equals PE final plus KE final. So we just need to pick our initial position, pick our final position, and write this out. And so we are starting, right, we're pushing, well, we have the equilibrium position drawn in here, but what we're starting and finishing from are the second two pictures, right? So the second picture is our initial position, and the third picture is our final position. And we're talking about Jack. We want to know how high does Jack go. So we're talking about where Jack is as being the final position. So we want to go ahead and fill in PE initial. PE initial, we've now got springs and gravity. So we've got 1/2, oops, that's not true. We've got springs and gravity. The potential energy is the potential energy due to the spring, 1/2 kx squared, plus the potential energy due to gravity, mg, oops, let's call it x initial, h initial, plus 1/2 v initial squared, plus the initial kinetic energy, equals the final potential energy, 1/2 kx final squared, plus the final potential energy due to gravity, final potential energy due to spring plus final potential energy due to gravity, plus the final kinetic energy, 1/2 mv final squared. So when we write out energy conservation, we just write out total mechanical energy, which is the total potential energy plus the total kinetic energy. Again, in this case, we've got both spring potential and gravitational potential. So this is PE initial, and this is PE, whoops, that was supposed to be an F, PE final. Okay, so now we just fill in what we know and what we don't know. So it was 1/2 K, we know the spring constant, just fill in with letters. Delta X is how far we've compressed the spring from equilibrium, doesn't matter whether it's up or down, it's how far we've compressed the spring from equilibrium, plus mg. And what is H initial? Well, H initial depends on where we measure H from. We can either measure H from the initial position, or we can measure H from the equilibrium position, right? So the two positions we can measure H from. This could be our H equals 0, or this could be our H equals 0. You need to decide. But since it doesn't matter, and I said in class that we're probably better off measuring H from the lowest position. If we measure H from the lowest position, then the height that Jack goes is actually going to be H plus delta x, the given H plus delta x. So let's go ahead and do that. Let's call this PE equals 0, so that therefore the initial height from where PE equals 0 is 0. Okay. What's the initial velocity of Jack? Jack's initial velocity starts from rest. Okay, starts from rest. Remember, we're asking how high does he go? That's initial. Final, 1/2 K. What is the final stretching or compression of the spring? Look at the picture. Is the spring compressed or stretched? The answer is no. So the final compression or stretching is 0. What is mgh final? It's the height above our 0. The height above our 0 is h plus delta x. So mgh final is h plus delta x. And v final, 1/2 m v final squared. What is the speed of Jack? Right? What is Jack's speed? V final equals, right? It equals 0. Jack stops. We want to know how high he goes. How high he goes is when he comes to a stop at the highest height. So that's 0. And so what we end up with is an equation that doesn't fit on the page, but once we take out all the zeros, 1/2 K delta x squared equals mgh plus delta x. This is actually the problem we had done in class the other day when we were doing a clicker question. Just looked at it from an energy point of view, energy conservation point of view rather than work energy point of view. And in the class the other day, we said let's just ignore delta x compared to h. In class the other day, we said ignore delta x compared to h, and then you can see that h is proportional to delta x squared. So if delta x is doubled, then h would be quadrupled. But in this case, we don't need to do that. So in this case, we've got 1/2 times 17, I'll leave off my units for speed, 17 newtons per meter times 0.02 meters equals the mass of Jack. Oh, I didn't give mass for Jack. I did give mass for Jack. And I gave the wrong delta x. Sorry, delta x is 0.01. Mass of Jack. Jack is small. Jack is a baby Jack. 0.02 kilograms times 9.8 meters per second squared times h plus 0.01. So that is what we get when we plug in the numbers and we solve for h. And what I get if I plugged in the values correctly, assuming I plugged them in correctly, I get h equals 0.42 meters. So h, the height above the platform in its equilibrium position, is 0.42 meters. How far does Jack go above his lowest position? Above his lowest position, it's h plus delta x, right? Above his lowest position is h plus delta x. So above his lowest position, it's 43.43 meters, 42 centimeters or 43 centimeters. But anyway, h, the height above the original position, is 42 centimeters.